Okay, so we want to discuss this concept. Probably the last concept is actually what I'm trying to work up to something called the expected value, and that comes in the context of discussing what are called probability distributions. So we want to talk about probability distributions, and we need to talk about this concept of a random variable. So we have these sort of three important concepts in probability: experiment, sample space, and event. And then there's also this other concept called a random variable. And so we want to talk about that. So let's imagine that we have so let's say we have the experiment of tossing a die. So what is the sample space? Well, usually I write it as we can get a 1, 2, 3, 4, 5, or 6. But I want to be a little bit more precise here. And I'm going to say, instead of that, I want to say that this is the sample space. So not the numbers, but the faces. So of course we associate this with a 1, this with a 2, this with a 3, and so on. But I want to focus on the sort of the physical outcome. So it's this face, or 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 this face. Now we could also do the same kind of thing with cards. So in that case, if we choose one card from a deck of 52 cards, we would get the sample space would be each of the cards. So it wouldn't be the number, whatever, the A or the 2 or the heart or whatever. It would be the actual card, okay, as opposed to sort of the number or the suit or whatever. So anyway, this is an easier one to look at because there's only 6 outcomes here. So this is what we mean by the sample space. And of course, normally we're just interested in the number of dots there. So for example, the number of dots here is 1, 2, 3. And so we don't even write the picture like this. We just write the numbers. But, there could be some strange reason where we're not interested in the number of dots. Like I'm just going to make up something like the distance, the closest distance between any 2 dots. So in that case, this wouldn't even, I guess this would have no dots. So maybe this would be infinity. There's no other dot close to it. Anyway, here the distance would be, say, this distance here. And here it would only be this distance. And here it would be this distance. And here it would be this distance, which I guess is the same as that distance. And here it would be one of these, this distance here, for example. So we might be interested in that. I can't think of why, but we might be interested in. Or we might be interested in like how many different rectangles we could form if we connected all the dots. So like here, if you connect all these dots all together, you have all the connections, you form a whole bunch of different rectangles. I'm sorry, I meant triangles. You form a bunch of different triangles. So you could count them up. And then here, maybe you form more triangles, or maybe not. Here, maybe you form more triangles, or maybe not. So that we might be interested in that, the number of triangles that you can form by connecting the dots. Now, I'm trying to think of anything else that we could do here. You might be interested in the size of the dots. Now, they're all the same size, but you still might be interested in the size of the dots. Or you might be interested in the color of the dots. Now, they're all the same here, but maybe they could be different. So you may not be interested, what I'm trying to say is, you may not be interested in the number of dots. There may be something else about the outcomes that you're interested in. So with that kind of thinking, we can introduce the idea of what we mean by a random variable. So I came up with these 4 different ideas. So first one is the one that we would always think of, the number of dots on the dice, on the top face. But I also came up with this idea, the minimum distance between the dots, the color of the dots, the number of triangles that you could form. So like, of course, here we'd have 1, and we'd have 2, and we'd have 3, and so on. And we would, of course, we would do this. This one goes here, and then we do this one. This one goes here, and this one goes here, right? This has 3 dots, this has 2 dots, this has 1 dot. Now for the minimum distance, I don't know. Like I said, I don't know what to do here. And maybe let's call this whatever, 1 centimeter. I have no idea what it is, but it might be, this might be, depending on the size of the dice, that might be 1 centimeter, and this might be like 0.5 of a centimeter, and this one might be 0.7 centimeters, and so on. So we would have, let's say, different color here. So we'd have, this would be 1, and this would be 0.5, and this would be 0.7. And then we could have the color of the dots. Now these dots are all black. So we would do this, maybe black. Oops. I guess I should make it black. Black. And then we could have like, so then we would have, this would go to black, and this would also go to black, and this would also go to black, because they're all black, and this would also go to black, and so on. So these lines mean what is, when we're talking about the number of dots, it means how many dots are there. When we're talking about the minimum distance, it means what's the minimum distance for each one of these. When we're talking about the color of the dots, we're saying what's the color for each one of these. Now they all are black. And then the number of triangles, I guess we could have 0 triangles. So where's 0? We could have 0. I should have made that black. We could have 1. We could have 2. I'm sorry, 2. We could have 3. We could have 4. We could have 5. I don't know how many is the highest number there. Maybe 7, and so on. Whoops, that 7 should not be there. I guess I'll put 7 here, and so on. So then, now this one has 0. Let's have a different color here. Let's say blue, and let's do this. So this has 0 triangles, and this also has 0 triangles, and then this also has 0 triangles. But then this one, I guess there's, let's see, how many are there? I think there's 4. If you do this and this and this and this, and connect all those dots, I think you could have 4. So this might be 4, and then I don't know what this is, probably the same thing, 4 again. I'm not sure about that, but I think that's right. And then here there's probably going to be more. So we have these scenarios. So what we're going to do is we're going to call each one of these, this one, number of dots. Oops. Number of dots is 1 random variable. Minimum distance between the dots is another random variable. The color of the dots is another random variable. The number of triangles is another random variable. So what is it? What do we mean by random variable? We mean that we take the sample space, and then from there we have some, actually, oftentimes we don't allow this example. So maybe I won't use this one, color of the dots, because usually this thing should be a number. So this is numbers, these are numbers, these are numbers, this is not a number. So let me rule out that one for now at least. So what we're doing is we're taking the sample space, and for each element we're assigning a number. And that's what we mean by a random variable. So we might be interested in the number of dots, but we can think of that as taking each one of these outcomes and assigning it to a number. Of course, it's obvious the numbers here, 1, 2, 3, 4, but that's not the only case of a random variable. We could have different random variable. That could be the minimum distance between the dots. So then we take each one of these outcomes, and that also assigns a number. This definition here, or this name, assigns a number. So the minimum distance assigns the minimum distance. And this one assigns a number 2, number of triangles. So this is 0 triangles, this has 0 triangles, this has 0 triangles, this has 4 triangles, this also has 4 triangles. So these are all examples of random variables. So mathematically speaking, a random variable assigns a number. Each one of this assigns a number. This assigns a different number. This assigns a different number to each element in the sample space. So we take each element in the sample space and we assign it a number. So like this number of triangles is a random variable, and it assigns, for example, to this element, it assigns the number 4. To this element, it assigns the number 4. To this element, it assigns the number 0. So a random variable assigns a number to each element of the sample space. And usually we're going to denote random variables, like we might call this one capital X, and we might call this one capital Y. So we usually denote them with capital letters. And this one might be capital Z, for example. Okay, so we'd have Z as one random variable, and we have Y as another random variable, and X is another random variable. Each one starts with the sample space and assigns numbers to each element, assigns a number to each element of the sample space. So that's what each of these does. Okay, so let's see what they say about random variables. They say, that's not exactly the way they talk about it, but I gave you a kind of mathematical description of it. Here they say a random variable is a numerical description of the outcome of an experiment. So that's another way of saying what I said. Now, we can talk about a discrete random variable, and we can talk about a continuous random variable. And we talked about this concept of discrete and continuous sets. So if you're talking about time, we call time a continuous variable. So for example, the time spent waiting for the bus, that's a continuous variable. And basically what we mean is, let's say you could wait 0 minutes, you could wait 1 minute, 2, 3, 4, 5, 25 minutes, more than that. But the thing is, you could not just wait 0 or 1, but you might wait a half a minute or 0.657 minutes, right? Anything is possible in between. In that case, when you have that kind of variable, that's called a continuous variable. On the other hand, we can talk about the number of people in this class, and then we might have 0 people, we might have 1 person, we might have 25 people, but we're not going to have 0.65887 people, right? Or anything in between 0 and 1. So that kind of variable is called a discrete random variable. So we have continuous random variables and discrete random variables. Now, I gave you 3 examples, X, Y, and Z. These are all So this one is going to be discrete because we can have 1, 2, 3, 4, 5, 6, and that's all. So there's nothing in between. And this one, the minimum distance, could be called continuous, except since we only have 6 dice, or 6 faces rather, there is going to be what we call a smallest distance between the two. So you could certainly argue that this is not continuous, that it's also discrete, and the same thing with this. This will be discrete. This will be discrete, the number of triangles that you could form. So anyway, we have 2 types of possibilities, something that's continuous and something that's discrete. And that's going to be true for random variables as well. So they say that a discrete random variable may assume either a finite number of values, so that's the dice. All of the examples that I gave with the dice actually are going to be finite. So that means it's discrete just because it's finite. Or an infinite sequence of values. That's like the number of people in the room or in the class. Maybe it's not finite, but you still never can have, half a person or something like that. Whereas if we're talking about time, that could be a random variable and it would be a continuous random variable. Okay, so in this rest of this discussion, we aren't going to talk about continuous, although we have talked more or less about that. When we use the normal curve, we didn't call it a random variable, but that would be an example of a continuous random variable, but we didn't call it a random variable. Okay, so now going back to this, now going to this. So let's take this example. So we have an appliance store. They sell TVs, and we're going to think about how many TVs they could sell in one day, and X can take on any of these values. So the random variable, we're talking about the random variable, and these are the values that it can take. And we can count the TVs sold, and there is a finite upper limit on the number that might be sold. And so that's going to mean that it's discrete, since there's only a finite number of different possibilities for the number of TVs. In this case, the highest number is 4. That's a little bit arbitrary. Maybe it's not really 4, but could be more, maybe. Okay, now, we also might think about this one. So we could say that it's the number of TVs. Oh, sorry, no, this is the number of customers arriving in one day. So we could have 0, 1, 2, and so on. So this is another random variable, and this is still called discrete. Now, I don't want to get too much into the distinctions between continuous and discrete. I think we have a basic idea, and we don't have time to go into all the subtleties of it. Okay, so here's some more examples of random variables. So family size. So let X be the number of dependents reported on the tax return. And that's discrete because it's the number of people. Distance from home to stores on a highway. So distance in miles from home to store site. So that's continuous because it's distance. It's going to be continuous. And then, does a person own a dog or a cat? So X equals 1 if no pet, 2 if dog only, 3 if cat only, 4 if both. So this is discrete. There's only 4 possible values. Okay, so now we want to talk about the probability distribution for one of our random variables, for our random variables. So let's go back to the examples we had. So we had 3 of them here. And let's go to the first one. And let's make a table out of this. So let's do this. These are the outcomes. And then we have the random variable. And our first one was the number on the face. Remember, we had the first one was here. That was here, the number of dots. So let's put that in there. So in that case, this would obviously be 1. This would be 2, and so on. So we could just do that. Oops. I just wanted to be lazy. Okay. So we could have, whoops, that didn't work. I guess I have to make this smaller. Maybe that works. Okay. So now we have the outcomes and then this. And next we put in, I guess I want to put next, I want to put in, I guess I'll do it here. So the probability distribution. Okay, so of course normally we think of this as 1/6. And whoops, that doesn't work, does it? I guess I have to do this. No, let's try that 1/6. Okay, you know what I mean? And this is also, they're all 1/6. Whoops, that didn't work either. 1/6. So these are the probabilities, 1/6. Now, maybe this is not a fair die, and these are not all equally likely, in which case we might have 1/6, or let's say, no, sorry, 1/9. We might have 2/9. And then we might have, let me just copy these. So they're not all equally likely. You can agree with that. This is probably, the first one is probably 1/9. The next one is probably 2/9. So they're not equally likely. But when you add these all up, you still get 1. You add all of these up, you still get 1. That was one requirement that we needed, and that is, we have that here. And then I could come up with other probabilities. As long as they add up to 1, they would all be different, we say different probability distributions for this random variable, the number on the face. Now we could make the same thing again. You can do that here. But instead of the number on the face, we could use a different example. So we could go to this one, the minimum distance between the dots. And there we only had what? I just made that up, but this was like, I don't know what to call these, minimum distance. Let's go to number of triangles. So number of triangles was 0, 1, 2, 3, 4, 5, 6. Say the maximum is 6. I don't know if that's true, but let's just say that that's the maximum number of triangles there was 6. So we could go 0, 1, 2, 3, 4, 5, I'm sorry, 7. Let's say we had that. So you could have 7. So maybe this one has no triangles, and this one has no triangles, and this one has no triangles, and this one had, I think we said 4, and this one also had 4, and I don't know what the last one has. Let's say the last one had 8. Maybe, well, let's just say 10. I don't know how many there really are, but let's say there's 10. So then we could say, well, what's the probability that there are? So actually what we want to do here is say that the possibilities are just 0, 4, and 10. So we don't need to repeat 0, 0, 0 when we're making this listing here. Just like here I didn't repeat anything, and here I'm also not going to repeat anything. So I'll just say the possibilities are 0. Maybe I'll put them over here. I'll make a new list. So the possibilities are 0, 4, and maybe the other one is 10. And those are the only possibilities for the number of triangles. Then we have to figure out what is the probability that, just get rid of this, somewhere else. So what's the probability that we're going to have 0? So how many ways are there to get 0? 1, 2, 3. So let's say that's 3 out of 6. Okay, and then how many ways were there to get 4? I think there were 2 ways. So let's say that's 2 out of 6. And then how many ways were there to get 10? Suppose this gave us 10 triangles, and this is the only one that gave us 10. So that would be 1/6. So this would be called the probability distribution for this random variable. For that random variable, number on the face. Oops, sorry, that's not number on the face. It's number of triangles. So for that random variable, which I think I called, what did I call it? Z, or number of triangles was Z. So this is Z, actually. I guess I should put this as Z. Z equals the number of triangles. Okay, for this random variable here, it's actually here. Maybe I should do that too. Move it over there. So for this random variable, these are the outcomes, and these are their probabilities, maybe. Now, maybe we could have other probabilities. but they always have to add up to 1, the probabilities. So over here, for this random variable, I think we called this x. X equals that. For that random variable, this one, these are the possibilities. These are the different possibilities. For this one, these were the possibilities. For this one, the probabilities would normally be this. This is what we would normally think of, but it doesn't have to be. It could be an unbalanced die. So it might look like this. And this one, this random variable. So the sample space is the same for both of these, but the random variable is the number on the face versus the number of triangles. So that's where how these are different. The random variables are different. And then their probability distributions are, maybe this one has this probability distribution, maybe this one has this probability distribution, or maybe it has this probability distribution. So the probability distribution says what's the probability for each outcome of the random variable. So what's the probability that it's a 5? 1/6. What's the probability that it's a 4? 1/6. But we could have a different probability distribution as long as they all add up to 1 and they're not negative. You can't have negatives. Then I might say, what's the probability of a 2? It might be 2/9. And what's the probability of a 3? It might be 1/9. So that would be a different probability distribution. So we have the random variable and we have the probability distribution. Okay, so we have the set of values for the random variable and the probabilities for those values. Same thing here. We have the set of values for the random, or actually it would be this, the set of values for the random variable. It just lists the distinct different possible values and their probabilities. Okay, so these were both the same experiment that was rolling a die. We had the same set of outcomes here, but the random variables were different even though we did the same experiment with the same sample space. Now we could talk about another experiment, which is to invest in a stock portfolio. So I don't know exactly what to put in here to make it similar to this. I don't know what to say, but I'm just going to skip to the random variable here. So the random variable, so let's say we might say we're going to invest, I forgot to say how much we're going to invest, but let's say we're going to invest $1 million. So the random variable might be how much it's worth after 5 years. Value after 5 years. Okay, so it could go down to 0. Maybe we're going to lose all our money. It could stay the same, or let's say no, it could go down to 4 million. It could stay the same maybe. It could go up to 10 million maybe. It could even go up to 20 million. Now, I'm just going to divide all the possibilities just into these 5. So obviously, could do a lot of stuff in between, but I don't want to write down a whole lot of stuff and I want to make it very simple. So let's just pretend that these are really the only possibilities that we're going to think about. Okay, now the question is, what do we do for this part? What do we do over here? Or I guess I have to write it here. What do we do over here? What do we do for the probability? Well, what we're going to say is we're going to go to some kind of expert in this stock portfolio, and we're going to say, what do you think is the probability distribution for these? And so let's say the probability that it goes to 0 is, let's say, 10%. And the probability that it goes to this is 0.2, 20%. And the probability that it stays the same is 0.3. And let's make this 0.2. 0.2. And the probability that, let's be optimistic about this. And let's say this is 0.3 and this is 0.2. Okay, so maybe this is what the experts this is sort of what we come up with for the probability distribution. Okay, so I don't quite know what to put in this column here. This was obviously just the physical outcomes, so I don't really know what to say here, but let's just skip to the to here, the random variable. So here the random variables could take on the values 0, 4, and 10. Here the random variable could take on the values 1, 2, 3, 4, 5, 6. And here this random variable is the value of the investment, so it can take on the values. We're just going to make it, like I said, simplify it. So we're going to divide it just into 5 possibilities. And we're going to say it could be 0, 4, 5, 10, and 20. And then this is the probability distribution that we came up with for this random variable. Okay, so where I wanted to go with all of this is, I wanted to discuss what we mean by a random variable, and we did do that. We said that we have a sample space, and we can go from there to numbers. So we could go to the number of dots. We could go to the minimum distance between the triangles. We could go to the number of triangles, right? So we start with the sample space, we go to these numbers. And then we said that there's continuous and discrete. And then once we have the numbers, we can talk about the probability for each of the numbers. Here, the probability for each of these numbers here. And here, I didn't know what to put here, but here I have the values or the numbers. So 0, 4, 5, 10, and 20 are like these numbers here, 0, 4, and 10. And then we have the probabilities for these numbers, and we have the probabilities for these numbers. This list is called the probability distribution for this random variable. This list is called the probability distribution for this random variable. This list is called the probability distribution for this random variable. This list is also called another possible probability distribution for this random variable. Okay, so now we finally get to where I wanted to go with this, and that is what we want to talk about this word, the expected value. The expected value for x, we want to talk about the expected value for z, and also, I didn't give this a name, but let's call this future. So let's call it future. Expected value for f. So I'm going to call this random variable future value. Okay, whatever, I'm going to call it f. Okay, so the f can take on these values, and these are the probabilities associated with it. Okay, now I want to talk about this expected value. So expected value is sort of like the word mean. We use the word mean many times, like the average, right? So expected value is sort of like that. So the idea is here. If you rolled the die many times and took the mean of all the numbers that you got, what do you think it would be, the mean, approximately? What do you think it would be approximately? So let's say we rolled the die. This is our die, and we are going to think about the number on the face. Let's not do this example. Let's do this example. So let's suppose we rolled the die and we got a 1 and a 3 and a 1 and a 6 and a no, I can't get a 9. 4 and a 4 and a 4 and a 1. Okay, so if we did that, if that's what happened, so how many times did we roll it? That's 8 times. So if we rolled it 8 times and we got those outcomes, what would that mean? What would be the mean of that? So what is this? This is 4 plus 1 is 5, 11, 15, 19, 23, 24. That worked out well. So the sum of these is 24. So the average of that is 24 divided by 4, which is 3. So we got a mean of 3. That happened to work out nicely. just by chance, we got a mean of 3. But here we only rolled it for 8 times. So what if we rolled it for 100 times? Then what do you think the mean would be? What if we rolled it for 1,000 times? What do you think the mean would be? What if we rolled it for 1,000,000 times? What do you think the mean would be? That's what we're trying to think about. So, well, since these are the possibilities, and if they're all equally likely, that is, if we have this distribution, probability distribution, then we're likely to get the same number of 1s as 2s, as 3s, as 4s, as 5s, as 6s. So, for example, if we only rolled it 6 times, we're sort of likely to get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. So if that happened, then what would the mean of those outcomes be? Well, then we'd have to do what? Add up these numbers. So instead of these numbers, we would add up these numbers if this is what we actually got. So that would be 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21. So we would get 21, and then we'd have to do 21 divided by 6. 21 divided by 6. This is going to come out weird. Okay. 21 divided by 6. And what is that equal to? That's actually equal to 3.5. Okay? So maybe that's what we should expect in the long run. That is, if we did it 1,000 times, 1,000,000 times, and so on. So anyway, you can see what happened, what I said happened here. And then I calculated the mean. It wasn't 3.5, it was 3. But thinking kind of theoretically what should happen, well, I sort of think that since I'm assuming the probability distribution looks like this, I should get 1/6 of the time I should get 1, 1/6 of the time I should get 2, 1/6 of the time I should get 3, 1/6 of the time I should get 4, 1/6 of the time I should get 5, and 1/6 of the time I should get 6. So basically what I'm saying is that I should get, let's see, suppose this is what I got. So what I can do is I can just organize these. So let's see, how many 2's were there? 1, 2, 3, 4, 5. So I'll put the 2's first. So I have 2 plus 2 plus 2 plus 2 plus 2. That's 5 2's. Plus, I don't have any 1's, but 3's, I have 1, 2, 3, 4 3's. 3 plus 3 plus 3 plus 3. And then 4's, I have 1, 2, 3 4's. Plus 4 plus 4. 3 4's plus 4. And plus 2 5's. I think that's what I have. Plus 5 plus 5. Okay, so that's what I got. In this case, I would do this. But then I can sort of count up the number of 2's. So I have 4 2's. So well, let's say how many 1's do I have first. So I have 0. Well, I'll leave that for the minute. So I'll say I have how many 2's? So it's 5 2's. 5 times 2 plus 4 times 3. 4 times 3 because I have 4 3's. Plus, how many 5's? 2 5's plus 2 times 5. And that's the same thing as this. And then I guess I could put in the fact that I have 0 1. So I could have 0 times 1 plus 5 times 2 plus 4 times 3 plus 2 times 5, 2 times 5 plus, we have 0 6's. 0 times 6. And then don't forget that to get the average, we don't just do this, we have to divide, we don't just do this, we have to divide the whole thing by the number of elements there, which in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. So I have to divide by 15. So that's what we were really doing when we calculate the average. So we'd have to do the same thing here. We'd have to divide this whole thing by 15. Okay, so let me do that. Divide by 15. But you know, in algebra, whenever you have something divided by 15, you can write each term separately and then divide by 15. So I could do 0 times 5, and then I guess I have to do this clumsily, but I could put divided by, and then I'd say 15 plus, I could say plus, and then I have 5 times 2 also divided by 15. So I'm allowed to take this 15 and put it here, right? And divide each term by 15. And then I could do the same thing with this term and this term and this term and all of them. So it's going to be this divided by 15, this divided by 15, this divided by 15, this divided by 15, and this divided by 15. So I don't want to write all that out, but it's going to be like that. Okay, then this was the number of times that I got a 1. This was the number of times I got a 2. This was the number of times I got a 3. So I could pull those out. So I could do it like this. I could rewrite this expression like 0 times 5. And then here I could put the 15 just over this part, right? You can do that in algebra. You can do the 15 just here. And then plus, and then you could do the same thing here. You could take just the 5 divided by the 15, and then times the 2. And you could keep going. So it would be 0 divided by 15 times 1, 5 divided by 15 times 2, 4 divided by 15 times 3, 2 divided by 15 times 5, and 0 divided by 15 times 6. You could do that. I don't want to write all of that out, but you could do that. Now, this is the relative frequency of getting a 5. This is the relative frequency of getting a 2. Now here I got, what percent of the time did I get a 2? 5 out of 15, which is what? Or what fraction is that? What's a simplified fraction of that? So 5 out of 15 is 1/3. So 1/3 of the time I got a 2. And 4 out of 15 times I got a 3. And 2 out of 15 times I got a 5. And 0 out of 15 times I got a 6. Okay, but if we did, so that's what happened when I just did it this minute, 15 tosses. But if we did it 100 times, I would expect that this 5 over 15 would get closer to what? Closer to 1 divided by 6. In other words, I'm saying that, yeah, I didn't get 1/6 of the time I didn't get a 2. That's when I just did it this many times. But if I did it 1,000,000 times, I would expect that the number of times that the percentage of times that I got a 2 is 1/6, the percentage of times that I got a 1 is 1/6, the percentage of times I got a 3 is 1/6, the percentage of times I got a 5 is 1/6, and the percentage of times I got a 6 is also 1/6. So instead of this times 5, why is it times 5? No, sorry about that. That was wrong. Sorry about that. I probably messed it up, confused you. But this is supposed to be 1, right? Times 1. So what I'm really saying is I should get 1/6 times 1, 1/6 times 2, 1/6 times 3, 1/6 times 4. Something's missing here. I left out the 4 here. And 1/6 times 5, and 1/6 times 6. So that's what I really think I should get if I did it 1,000,000 times. So that's what the average should be. Now, where does that 1/6 come from? That 1/6 came from here. In other words, so what I just said I should get, what am I expecting here? I'm expecting 1/6 times 1 plus 1/6 times 2 plus, and then I'll just go plus, then I'll go dot, 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 plus, and then the last term is going to be 1/6 times 6. So that's what I'm expecting to get if I do it 1,000,000 times. because I expect each of these to happen 1/6 of the time. So this is what I expect to get. And this is called the expected value. Remember we said we want to talk about this thing called the expected value, and I said it's kind of like the mean or the average, and it's the mean if you could do this millions and millions of times. If you could do it millions and millions of times, I would expect 1/6 of the time to get a 1, 1/6 of the time to get a 2, 1/6 of the time to get a 3, and so on, up to the 6th time. Now, why was it always 1/6? Because I assumed the distribution looked like this. If I had assumed the distribution looked like this, then I wouldn't think this is what the expected value is going to be. That means the long run mean. I wouldn't think that's what the long run mean is. I wouldn't think that's what the expected value is. So what would I think? I would think it's going to be not 1/6 here, but 1/9 here, 2/9 here, 1/9 here, and so on up to 2/9 here. So what we see is that the expected value comes from taking this, the value of the random variable 1, times its probability, and then 2 times its probability, and then 3 times its probability. So if we didn't have these probabilities, if we had these, then we would take 1/9 times 1, 2/9 times 2, 1/9 times 3, and so on. In other words, we take 1/9 times 1, 2/9 times 2, 1/9 times 3, and so on. So what we're saying is to get the expected value, you do this. What did we do? We take each x and multiply it times its corresponding p. That's what I mean by this. I mean, you take each x and multiply it times its corresponding p, and you sum them up. That's what we have here. We have the x times its corresponding p, the x times its corresponding p, the x times its corresponding p, and you sum them up. That's what this means. Or if it was this set of p's, then you take the x times this p, the x times this p, and you sum them up. So anyway, this is what we're doing. And this is the expected value for a random variable. So the random variable is here. This is the random variable. This is the probability distribution, or it might be this one. And then you do this to get the expected value. And that's what you expect. And that would turn out to be this number here, 3.5 in this case. For this random variable, for this probability distribution, for this random variable, it would turn out to be 3.5 if we use this one. Okay, here I don't know what it would be. I guess it might also be 3.5 actually. But whatever, that's called the expected value. And we also write it like this. The expected value of x is this. If it was z, if we were using z, it would be the expected value of z is sigma p z. You'd have the values of z, so it would be these values here, there'd only be 3, and the p's would be these probabilities, and that would tell us the kind of expected number of triangles to get when we roll a die. How many triangles sort of on average do we expect to get? Now notice we never get, in this case here, we never get 3.5 for this. We get 1, 2, 3, 4, 5, or 6. So the 3.5 never even occurs. The expected value is 3.5, but it never even occurs. It's just sort of like an average of all of these. It's actually a weighted average. That's what this is. It's a weighted average, and it's weighted by these probabilities, or it's a weighted sum weighted by these probabilities. Now going back to this one, oh, and one more thing. This is one notation, e of x, but we also use this. The expected value of x, we can use mu, we can use this symbol, and this is how we calculate it. So let's do one last example of this. So we've covered now the expected value, and here's a kind of interesting application of it. Let me just move this thing down so we know what it is. Okay, so here's a kind of interesting application. So what did we do to calculate it? We took each outcome of the expected value. Remember, there were this, this, and this, or it could have been just 0, 4, and 10. And here, these are the outcomes. You could have $0. You could have 4 million, 5 million, 10 million, 20 million at the end of 5 years after you invested I think I said you invested 5 million. So this is what the experts say could happen with these probabilities. So what's the expected value of this investment? So what is the expected value of this investment? Well, we do it like this. That is, we take the outcome times its probability, the outcome times its probability, the outcome times its probability. Or here, we take this outcome times its probability, this outcome times its probability, this outcome times its probability, 10 times 0.3, and 20 times 0.2. And we add all of that up. So we're going to get like 0 times 0.1. What is 0 times 0.1? That's 0. And what is 4 times 0.2? That's 0.8, right? And what is this times this? That's 2/10 of 5. It's 1. Sorry about that. It's 1. And this one, 3. And this one, we do this times this, 4. Okay, so we took this times this, we got that. We took this times this, we got that, and so on. And then we did each of these individually, then we have to sum them up. We have to sum this up. So let's use this. And so according to the experts, our portfolio after 5 years should be worth $8.8 million. Now, notice that according to the way we set things up, it's never going to be worth 8.8. It's either going to be worth 20, 10, 5, 4, or 0. So this is just sort of like the average or the expected value, the mean of this. So what did we just do? We actually, if we want to write an Excel formula for it, we took this times, now I can check my calculations, this times that, and then actually I can just drag this down. Did I get them right? Yeah, I got them right. And then we sum them up. So, and we get 8.8. So you could write this formulas like this. Anyway, that's the expected value for this investment after 5 years. Okay, so let's compare that with another investment. Let's do something like this. Just copy this. But let's change the values for the outcomes. So let's change them to this. So this one is a little bit more conservative in the sense that it doesn't go down to 0, but it doesn't go as high either. So not quite as good on the high end. And we could change these probabilities, but let's just leave them. We're just making up an example. And now we do the calculation. This is the automatic calculation. This is the old calculation, so it's not related. And now we can see that this one, the expected value is 9.3, whereas the first one we did, the expected value was 8.8. So this one has a higher expected value. And although we're not going to talk about it, we could also talk about the variation or the standard deviation or the variance of this as well as compared to this. So there would be a way to measure the variance of this one, and that means kind of the volatility or the spread of the investment. So this one most probably has a greater variation because it goes from 0 to 20 and as compared to this one. So this one has less variation and actually a higher expected value. So they may have some effect on how you would like to invest or on which one you would prefer to invest in. So let's go through this quickly and see what they say here. So a discrete probability distribution. So we said that when we sum up all the probabilities, we have to get 1. And we also mentioned that each one cannot be negative. So going back to ours, we had this picture, and when we summed all these up, we had to get 1, or here we get 1, and we can't get any negative numbers here. So they're calling this thing f of x. F of x. Okay? And f of x, when you sum them all up, you have to get 1. And actually, I think they should call it p of x, or maybe they don't have to, but we've been calling it p, or p of x, they're calling it f of x. Okay, so it has to be greater than or equal to 0, and when you sum them all up, you have to get 1. And let's keep going. Okay, so here they have these probabilities, and I guess when you 0.4, 0.25, 0.20, this is the number of units of TVs sold, and they expect from the past data that 40% of the time they don't sell anything, 25% of the time they sell 1, 20% of the time they sell 2, 5% of the time they sell 3, and 10% of the time they sell 4. So this could be the probability distribution here. And then, of course, it has to sum up to 1. And we can also graph this. So we could say, we could have the x-axis be 0, 1, 2, 3, 4, and then put the probabilities, 0.4, 0.25, 0.2. So that looks like this. So 0, 1, 2, 3, 4, and then we have the probability of 0, probability of 1, probability of, I don't know, wherever, 2. I guess this is 2. Oh, I think there was 0. What was that? Why is that? Well, whatever. Probability of 0, 1, 2, 3, 4. Yeah, it doesn't look very good there, but you could do this kind of. So this is the probability distribution of how many TVs they're going to sell. This is a picture of that probability distribution. So let's just go on. Okay, variance and say, oh, here. So the expected value, E of x, is x times p. Or, if you're using f instead of p, it's x times f. So that's the expected value, also called mu. Okay? Okay, let's stop with this. So we have covered the expected value. So we covered enough probability to cover this concept. Okay, so I really wanted to get to this concept, expected value, and we needed some probability to do it. So we did some parts of chapter 4, which was just on probability, and then chapter 5 was on random variables. So we needed to discuss what we mean by a random variable. And I don't have that here right now. Here it is. So we said, mathematically speaking, a random variable assigns a number to each element of the sample space. So here's the sample space, and we have these numbers, the number of triangles. We had the number of dots. We had the minimum distance. So those are random variables, and we said they could be continuous or discrete. So we discussed that, and then with that, we are ready to discuss the concept of expected value of the random variable. And there were many different choices because we have different we had for example, this probability distribution, we had this probability distribution, so we could get different expected values. We could have a different probability distribution as long as they all add up to 1 and none of them are negative. That would be another we could have other possible probability distributions. Here we have these are the different possible number of triangles, and we could figure out, if we didn't do it, but we could figure out the expected number of triangles. How would we do that? We would say this equals this times this probability, and then we could just copy this down, the formula, to here, and then sum these up, and if we sum them up, that didn't work. Why not? Oh, because I used this. Oh, this worked over here. But here I'd have to say, I guess I have to say 3, 6. See if that worked. Can I write that? No, I have to say equals 3, 6. Equals 3, 6 equals, it was 2, 6, and equals 1, 6 equals 1, 6. Do that. Okay, now I get this. And the expected number, we might have 0 triangles, we might have 4, we might have 10. And the probability of 0 is 0.5. Probability of this, 4 is this. Probability of 10 is this. The expected number is 3. Okay, so anyway, we discussed expected value. We did it just now for this example, but we also did it for this example where we figured out these are the different values of the random variable. These are the probabilities that the experts told us. We multiplied these times these and summed them up, which means we did this calculation here. And in the book, they use, instead of P, they use F. But whether we use F or P, this is the calculation. So we did that here. And we found out that the expected value of this investment, according to the experts, was 8.8 million after 5 years. That's when we invested 5 million.